Hey guys, it's Mr. Marone. Welcome back. Today we are going to start the second chapter in our year so far, and we're going to start with the first section on inductive reasoning. This chapter is going to be all about reasoning and proving or proof in regards to mathematics. So up to this point, you've been able to do a lot in math in regards to problem solving, but haven't had to give reasons why you're doing the actual steps. That's what we're going to look at throughout this chapter, is being able to not only complete the math, but to show why we can do what we do. There's going to be multiple types of reasonings that we're going to look at. Today we're going to focus on inductive reasoning. Okay? And to give you a definition of inductive reasoning, it's when you're given a pattern of numbers, of shapes, of anything like that, being able to reason or come up with a conclusion based on that pattern is going to be inductive reasoning for us. And like I said, we're going to have some number patterns, we're going to have some geometric patterns. It's going to be a mix of both. And ultimately, our job is to draw conclusions from that. Let's take a look at our first two. So it says look for a pattern below, and it wants us to find the next two terms. So if we look at the mathematical one, that first one up here, we see that it goes from 3 to 9, from 9 to 27, and from 27 to 81. If I think about it, I can get from 3 to 9 by multiplying 3. Okay? I can then get from 9 to 27 by multiplying 3. And I can get from 27 to 81 by multiplying 3. So there's my pattern there. I'm going to multiply each time by 3. If I were to do that one more time, multiply by 3, I would end up with 243. And they asked for the next two terms, so we're going to do that one more time, times 3, and that's going to give us 729. So those would be the next two terms in the pattern. Now in this bottom pattern, this is a geometric pattern. So if we notice, we've got a circle with a triangle inside of it. Then we've got a circle with a square inside of it. Then a circle with a pentagon inside of it. So we started with a three-sided figure. Then we went to a four-sided figure. Then we went to a five-sided figure. So the pattern is going to be to add one side each time. So now as a real test of my drawing abilities, we're going to have a circle with a hexagon inside of it. So 1, 2, 3, 4, 5, 6. And then we're going to have one more circle with a seven-sided figure in it. So 1, 2, 3, 4, 5, 6, and 7. Obviously not drawn to scale, not as well as they did for us, but it's about seeing the pattern, seeing that we added one side each time. So at this point, I'm going to encourage you to pause the video and to try to figure out these next two terms in your notebook. So hopefully you're coming back out of a pause here, and we're going to look at it and see that in our first pattern, we're subtracting 5 every time. Subtracting 5. So we would then be able to subtract 5 and get 25 and 20 as my next two terms. In our bottom one, they have a rectangle, then they're drawing in a diamond in the second one, then a rectangle inside the diamond. So the next two would be rectangle with a diamond inside, with then a rectangle inside of that, with then a diamond inside of that. Okay? And if I were to do number 7 or number 5 in this pattern, I would add another rectangle inside of this. Okay? So it gets trickier and trickier to draw, but each time they're adding another figure. Okay? Now, we've got something in mathematics that we call conjectures. Okay? And we want to find something other than just the next term. We would use a conjecture. We would draw a conclusion based on what we were able to reason, the pattern we were able to find, anything like that. So here's an example for you. So look at these circles. What conjecture can we make about the regions that are in the circle if we had 20 diameters drawn in? So in this first picture over here, we have one diameter and it breaks the circle into two pieces. Here we had two diameters and it broke it into four pieces. And here we have 3 diameters and it broke it into 6 pieces. So if we think about the math of this, there was 2 sections times the number of diameters gave me the number of sections total. So I've got the number of, and we're multiplying by 2 each time. So every time you were to draw a diameter, and it would split it into 2 parts. So in this case, 2 times 2 diameters gives me 4. 2 times 3 would give me 6. So if we had 20 diameters, 2 times 20 would give me 40 sections of my circle. So thinking about this is another great question. So what conjectures can we make about the sum of the first 30 even numbers? So if we think and just make a quick table, I'm going to give you the table, but think about it for a second. So if we had one term, that would just be 2. If I had two terms, it would be 2 plus 4, which gives me 6. Then I'd have 2 plus 4 plus 6, 2 plus 4 plus 6 plus 8. Okay? And you see over here the sums. Okay? And what was concluded about the sums if we were to be doing a multiplication here? So they gave us that 2 would be 2 times 1, 6 would be 2 times 3, 12 would be 3 times 4, 20 would be 4 times 5. Okay, so we have 4 terms, and it's going to be 4 times 5. So the pattern is that it's the number of terms times one more than the number of terms. Okay, see that here? So it was one term, so 1 times 2. 2 terms would be 2 times 3. 3 terms would be 3 times 4, and so on. So if we wanted the first 30 even numbers, we would do 30 times 1 more, or 31, which when calculated out gives us 930 as our total sum here for those first 30 even numbers. Okay, so you see, if we really wanted to find the pattern, we could work all the way down and add the first 30 even numbers, or we could try to draw a conjecture from that pattern, from that reasoning that we're able to do. So the last piece for today is what are known as counterexamples. So something that's very important to know is that not all conjectures that we make are going to be true. The nice part is that when it comes to proof, if you make a conjecture, you have to give lots and lots of examples, or very sound examples, as to why it works. But with a counterexample, you're just finding one example that shows that a conjecture is false. Okay, so you have to keep proving yourself when it comes to a conjecture, but with a counterexample, you only need to find one specific example. Okay, so I've got 3 here that I'm going to show you, and let's try to come up with some counterexamples. So the first one is if a month starts with the letter J, then it is a summer month. Well, if we think about it, we have June and we have July, but we also have January, which is very much a winter month and not a summer month. So January would be our counterexample. Even though there are summer months that start with J, there is one that's not a summer month. So that would be our one counterexample that makes this statement or this conjecture false. Okay? Next one, it says you can connect any 3 points to form a triangle. Well, I could make point 1, point 2, and point 3, and I could connect those and make my triangle. Okay? But what if I put 3 points together? What if I put point 1, point 2, point 3, and those are collinear? Okay, those are 3 points, and I can't connect those to make a triangle. There's no way I could do it. And the last one says if you multiply any number by 2, the product is greater than the original number. Okay, so we could calculate out and calculate out, but if we think about it, what if I did 2 times 4, which gives me 8, but then I multiplied 2 times negative 4, and I had negative 8. And what if I had 2 times negative 6? That gives me negative 12. Well, if you think about it, I've multiplied these two numbers, but negative 12 is not bigger than negative 8, right? Negative 12 is more negative than negative 8, so that doesn't work. So this would be one counterexample right here for us. It only takes one. So that pretty much wraps up the lesson for today. Make sure to answer the questions and fill out the Google form, and we will talk about the rest of this in class tomorrow. Have a great night, guys.